Hello everyone, I'm Illia coming back with Whiteboard series here from New York. I have Tarun from Gauntlet Network and we're gonna go in to the MEV.
Yeah, so I think if you follow crypto Twitter at all nowadays, there's a lot of fighting over what qualifies as MEV. But first of all, let's write out what the acronym is. The acronym has changed. It actually stands for maximal extractable value, not
because no more miners.
Right, exactly.
As of a few weeks ago.
Yeah, exactly. So this is what we're talking about. And so, the problem is, one, hard to define. Two, it has the quality of porn, which is you know it when you see it. This is from a famous Supreme Court case where this was
the definition of
porn.
Nice.
But you know it when you see it. Unique to blockchains, because in TradFi you don't really see it. You see your version of it, but the exchange doesn't tell you really what everyone else is doing.
Yeah.
So it's hard to see if someone is extracting something from you. But here it's like porn because you literally go in the Block Explorer.
Yes, but you have like Robinhood, for example, which was kind of doing that, right? Like you send all your trades and they would match them and kind of do it.
But you don't actually see how much
money they made out of this.
Exactly.
Yes,
you don't really see how much Citadel made out, or Jump, or whoever made out of it, right? So the interesting thing is that here in blockchains, there's this porn aspect of it in that you can go run the transaction and see how much it should have cost or taken, and you can go look at what actually happened, and you see a difference. So clearly, there's some sense in which difference between expected cost and realized cost. So, this is, I send 5 tokens. I'm supposed to get $5. But I get $4.50.
But then you also said you're fine with this when you were sending here, otherwise it would have failed.
Correct. But the thing is, in a lot of applications, right, an application will guarantee you something. It'll say like, spend $5 on Robinhood and you'll get 5 shares. And then if you say yes, and then you see that you got 4.5 shares, you'll be pissed.
Yeah.
So this is the you know it when you see it aspect, right? Now there's this big question of like, is everything MEV? So, I think the Flashbot people who do MEV auctions on Ethereum, I think they take a lot of liberty with saying even like our DEX arbitrage is MEV. But in some ways, it's not really. It is just intrinsic to the system that there's some uncertainty over a block, and whoever gets kind of to pick what the block ordering is kind of has some power over the users. So instead, I think a sort of more kind of economic way of defining MEV is sort of, we have a sequence of transactions that are sort of sitting in the mempool. We have a sort of value function which takes in a ordered sequence of transactions.
And you want to find such permutation?
And you want to say like, what's the max permutation? So this is the permutation.
It's probably going to be the most formulas in Whiteboard series thus far.
Right. This is MEV. or sorry, rather, you should say this is the max value, M. This is the expected value, E. Expected value, permutation.
So, but here's a question for you.
Yeah.
Why don't block producers by protocol not forced to just randomize this order?
Yeah, great question. one reason is that they cannot come to consensus on the actual transactions they have. So for instance, if we have a network of validators, I'll just draw them as, this network graph. These are the validators. And then there's the network of users. Actually, you mind if I use the other color? Thanks. So we'll make the red as validators. Blue is users. And so, the users are sitting all over the internet, and they submit transactions. And as you can see, they submit them to different validators. Maybe they submit them twice, just to make sure their transaction gets in. And the problem is coming to consensus on the set of transactions you have. So on the set TX1, A, adds a bunch of latency, but B, if you basically have to ensure that people are not dropping some of these transactions. But also, you basically have to do what's sort of like a ranked vote. So if let's say even if we agree that these are the transactions, the set of transactions, the ones we're going to include, then we have to say, okay, well, I got this transaction first, and I got this transaction last. But the problem is there's no way that everyone gets the same ordering.
Sure, yeah.
Right? And effectively, people have to vote on what the ordering is. They could vote on the randomness, so they could vote on but the thing is that the randomness only chooses the permutation. The way each person is storing the set is actually up to them.
No, but I mean, you can say publish a set first, get to a consensus, and then through that also vote on the randomness. Like, for example, the randomness is sourced from the ELS signature on the block, and then the execution happens already.
So we need to agree in advance on some notion of what the set is and what lexicographic ordering is, what alphabetical ordering is, so that and then we draw this random permutation, right? A, higher latency. B, you still have the set problem of how do you guarantee that people are including what they say? Because
you mean that this is where the tips and transaction fees are coming from to actually get included and privatized.
Yeah, exactly.
And so as soon as you do that, you're kind of violating the.
And B, that there isn't some side channel agreement where a miner is accelerating certain transactions versus others, right? Which is what Flashbots effectively, does. There's an auction, you pay them. If you win the auction, you get to go ahead of everyone. So, A, it's bad. B, increases latency. C, sort of increases communication that the validators have to do, makes them more susceptible to get DDoSed. There's lots of sort of things that make it harder. So instead, the way things work on Ethereum right now is there's effectively a centralized coordinator called Flashbots. And let's say I'm a strategic user. So I'm going to call the strategic user is going to give them a face with some glasses. And the strategic user is like, hey, Flashbots, here's my transaction, and I want it to be first. And I'm willing to pay $5 more than what the transaction costs. And let's say that wins, then Flashbots broadcasts this transaction
to all the
validators, and who subscribe to it, and they effectively agree like a cartel to execute the transaction such that that occurs, and they only get the payment if the thing
passes.
And so you might say, hey, I'm getting robbed here because this guy's putting his transaction first, so that when I put in the 5 tokens, I only get 450 because he put in his 2 tokens before and took out my 50 cents. Not great. But arguably, it is more efficient in the sense that people who are strategic, who, if this wasn't there, they would try to spam the validators with many, many transactions, and you would actually get worse performance in other ways.
The whole network, yeah.
Right? So there's this trade-off between the economics of incentivizing the strategic users to pay more versus the spam on the network. And that's sort of this intrinsic trade-off in MEV. There's people who spend their lives trying to make these things called fair ordering protocols that do really complicated, kind of the things we talked about, like everyone keeps voting on the sets of transactions first, then they vote on sort of the randomness, and then they execute. so far, none of them have worked without either some amount of centralization, they have sort of some fallback mechanism, or they just blow up
take forever,
right? So,
like some consensus algorithms
the big problem is no one has actually proven any formal results about this that say something like, hey, there's always this trade-off of like, you either get the highest information processed through your blockchain, or you have to slow it down to like guarantee some sort of fairness, and there's sort of some trade-off curve.
There's a latency pretty much. Like everything is about latency.
It's sort of latency
for finality or for
sort of cost and sort of fairness measured in some notion of like how much you're respecting like the intent of the user. Because like one way of thinking about it is we have a blockchain, block 1, block 2, block 3. The user sees the state at block 3 and it sees that it's like $5 for a shitcoin, right? And they're like, oh, I want to buy $5 shitcoin. And so I'm like, yeah, I'm going to send my transaction. Here, take my money for $500. But then, you know, of course,
somebody comes in
and they instead of getting 100 shitcoins, they only get 90. And so, you know, the idea here is that fairness would say, hey, actually, if there's 10 people trying to get the $500 thing, instead of having one person get it 100, another person get 95, another person get 90, split it evenly. That's the fairness axis. The latency axis is like, how fast is my transaction going to process?
Yeah, just aggregate all transactions, wait for a while.
Exactly.
Everybody chill, and then settle on fairly.
Exactly. And cost is a little bit complicated, actually. So one thing that's interesting is like, suppose we have two exchanges. So we have one exchange that shows $5 shitcoin, and the other exchange that shows $4.50 shitcoin. What's the real price?
Well, it depends on how much you're buying and the depth of the pools.
Exactly. How much liquidity there is, what you're buying. It's possible that the $5 shitcoin is horrible for you because there's no liquidity and you push the price to $10. Or it's possible that the $4.50 is actually worse. And so what is the natural incentive for people to do is to synchronize these, because technically they have the same assets. So, you know, buy low, sell high. So in some sense, your cost goes down by allowing people who are doing arbitrage to go in front of you, because they're actually ensuring that the prices are sort of synchronized, and so it's as close to $5 as when you saw as possible. And so that's sort of, there's some sort of like surface in this 3D, I'm bad at drawing 3D things, but there's some sort of trade-off surface between fairness, latency, and cost. And there's this idea that like, hey, if I maximize the people who believe in fair ordering, they think that if you maximize fairness, you're not trading off these other two. But I think that like one of the big unsolved sort of mysteries is proving that you can never have all three of these.
But I think, I mean, the question is also, because for example, you build a blockchain where there is, the swap is a core part of protocol, and you can have like, you aggregate all the transactions and then you execute swaps at the end of the block, right? Like you can have a more, like the transaction ordering, for example, does not matter in a block at all.
Yes, so there are things like Penumbra, which is a ZK blockchain, where they take all your transactions and they do a batch auction. So the batch auction gives everyone the same price. So it maximizes the fairness side, but everyone actually only sends encrypted transactions. So liquidity providers have to play this game where before the block, they have to basically submit how much of their liquidity they want to keep for that block, and then the order flow gets executed privately against that. So in that's another example of someone going way on the fairness axis, but like their latency axis is also quite low. They're high fairness, low latency, but high cost, because the batch auction worst case is high cost, right?
But let's say you don't do it private, you do it in public. You say we aggregate all transactions, and instead of executing them in order, we batch all the orders.
But now your consensus rule has to interact with an application for the order.
Well, but then let's say we build a you know, the fair, low latency, low cost swap chain.
Right, but my point is you can't drive all of them to zero, or like maybe inverse. There's some sort of like limit to how well you can do without making your consensus suddenly.
Well, I think that what will happen in this case is that the cost is lower on Ethereum, for example, because there's so much more other stuff. And so as soon as you start optimizing just for swaps, a specific chain, you lose all the other functionality, and now actually your cost will be higher because you don't have like flash loans and stuff like this to like actually.
Or you don't have routing where you have many dexes, and I can, I want to trade A to D, but I can split my trade into A to B to D, A to C to D. Yeah. And actually, this gets to a paradox in a paper we wrote recently that's actually pretty easy to explain, that you can explain mainly without math by just some pictures.
Wait, Tarun explaining something without math? What?
I do my best. So this is a sort of paradox basically in this paper, we found this paradox, that the inverse of this paradox that exists in sort of traffic modeling, like when you're designing cities or designing roads between cities for AMM. So the way it works is, imagine we have 4 tokens. Unfortunately, there's not. I don't know shit in other languages. Otherwise, I would name them each a different form of shit. But we'll start with the traffic version of this. So we have 4 cities. On each edge, so you want to go from A to D. So you can go A, B, D, A, C, D. On each edge is what's known as sort of the latency. So let's say there's 100 cars that need to travel this. If the latency says X, then and 50 of the cars take this route, then the time it takes is 1/2. Mm-hmm. And if it says 1, it's like infinite. It's like a really large highway. Mm-hmm. It'll just take everyone the same amount of time, always. And so we have this thing where we have, kind of this really large highway, really narrow road, really narrow road, really large highway. Okay, so if we look at the equilibrium of this, imagine everyone was like, hey, like, what's the fastest route to take? Well, they would see, okay, well, it takes me the same amount on each route, and you would expect traffic to sort of 50-50, right? So you get 50-50, 50% this way, and 50% this way. Okay, now imagine, counterintuitively, that you add a road here that has latency 0. Mm-hmm. Just imagine a teleportation device, right? And so, actually, by the way, when they're split 50-50, the time it takes you is 1/2 plus 1, which is 3/2, right? Because half goes here, so 1/2, and then it takes 1. Okay, now here, if everyone is selfishly optimizing, the fastest path is actually this path. Yeah. Because if they took any of the other paths, it could be higher, right? But here, it's actually technically, X and X, whereas this is always 2, and X is less than 2. So basically what happens is, but then you get this weird paradoxical thing. If everyone takes this route, then the time it takes them, even though I added another road, there should be more throughput in the network. The network should be more efficient. Takes them longer, because like everyone took this road and everyone took this road, it takes time too. Right? So that's bad. However, what happens if I add now? Let's suppose I add a
0.1,
a little epsilon times x. That's the only symbol you're getting. Okay. So now, as you make this like congestion cost go up, then you'll see that people will revert to distributing 50-50, and like how much this congestion cost controls like how people distribute themselves in this network. AMMs are the same way. If I have 4 tokens, and I have these edges that can be built. It turns out that these people doing this MEV, there's this thing called sandwich attacks, which we can explain. I don't know if that's worth explaining.
I mean, we can.
It's sort of this idea of I put in $5 tokens. I'm supposed to get $5, but I get $4.50. And the way it works is basically, any trade you put in, you say, okay, I'm putting in 5 tokens, but I don't want to move the price more than 10%. And I say the percentage. But let's suppose someone who's strategic notices that actually, if they put me first in the block, I'll only move the price 5%. Then they add another transaction. So this is, say, attack. They call it a sandwich attack. It's not really. I find it hard to call these things attacks. They're sort of like,
it's a sandwich trade.
It's like you're a bad, dumb user. Like you should have been bidding in the auction for the same spot, but like you're willing. That's what you get for being the unsophisticated user.
You're just saying order books are better.
I'm not Anatoly, so right. So this guy adds in a trade that pushes the cost up 5%. we put in my trade, which pushes the cost up 5%, and then the attacker sells back. So attacker sells back their amount that they put in. And so this sequence of trades can be profitable. So they push the price up in front of me. I get a worse price. I get less tokens out. And then they sell right after me. And as long as they can guarantee these are executed in that order, they can take advantage of me. Now, the interesting thing about this example is the sandwich attacker is adding this congestion, epsilon x, in some sense. And what actually is kind of a very non-intuitive thing is that without the sandwich attacker, there's some scenarios where, based on the different relative liquidities of this, where actually you have a worse cost for executing end trades over this network than you do if you have the sandwicher. So the sandwicher actually, they cause congestion, but they kind of, in the same way, they make people's routing go back more optimal. So there's this trade-off between, like, yes, the users who take that edge are getting sandwiched, getting a worse price, but the overall flow across the network can be better. And there's this trade-off between congestion and routing costs.
So, but usually this kind of trade is atomic, and so, like, even if it is, like, if it's sandwich, like, let's say my trade is, A to B to D plus A to C to D in one transaction.
Yeah.
And so you're saying that, like, they've done this on, like, AB and on AC, for example.
Yeah.
And then sold it. That's still.
In some cases, that it's not always true.
Yeah.
It's just that there are examples where if this thing is actually sort of low liquidity, but these are higher, then and there's some ratio between how much liquidity is here. You can basically get this scenario where the sandwicher actually helps avoid people taking the low liquidity path, because the sandwicher's profit is highest on the low liquidity path, so people's routing changes around.
I see. But this is, like, presumably when somebody doing the search, they should probably try to predict how much they're going to be extracted.
If someone's doing the search, if there were a way to do this in Ethereum, you can't do this. But I think if in anything where you have multi-transaction flash loans, you could actually just flash borrow B and C, add liquidity here, and then actually make the path cheaper. But you'd have to inject the flash loan inside the atomic thing. So it would be annoying. So you'd have to do this multi-transaction MEV of, like, flash loan, execute trades, unflash loan, right? And it's hard to compress those atomically. But if you could do that.
No, if you had resources, for example, that are multi-block resources
exactly,
that get
with
back.
some guarantee, Then you could actually just never have any of these types of problems, and just assuming there's, like, a flash loanable place.
Capability,
Yeah.
Yeah, this is actually something we wanted to do because our stuff is always multi-block anyway.
Right.
And so we've been thinking how to have, like, pretty much resources or vaults where
you actually walk me through how the design of that. How do you guarantee kind of atomicity?
We don't.
Over these.
Each contract is almost its own chain, or its own rollup, or its own subchain, or its own parachain, or its own, like, name a thing.
Even within a chain, what I'm saying is.
But within it, that's the point. We don't have, like, each so let's say you have, like, Uniswap. So on near Uniswap has all the pairs in one contract.
Okay.
And so then it's called refinance. And so then all the trades are just linearized around that. But if you want to do anything else, like, for example, actually send tokens to the user, that is done in the next block. So the token itself, like, USDT.near or whatever it's called, is like, you deposit money in one block, and then you do a trade, and then you withdraw. In a way.
But you can't do that all in the same block?
No.
Okay.
Because each cross-contract call happens in the next block.
The cross-contract call is the token.transfer call for USDT.
Exactly. So it's all based on callbacks. You're always calling it's message passing, right?
Am I guaranteed my callback doesn't revert? Like, what happens on reversion?
You get a callback.
You get but then you have to wait another block, right, for that callback to have the exception. Yeah. Does the exception ever take more than a block?
No.
Space. You guarantee that?
Well, we have gas limits, so you can write some code that will run out of the gas.
Yeah.
But so you kind of need to guarantee the if you
want
to
go
go back
meant someone can't make an exception that throws an exception callback and, like, has this chain of like if they wanted to grief you because you're paying the gas for that?
Well, so the user pays, like the whole transaction is paid by the user, right?
Right,
So
the user would, but the user could trigger this chain of exceptions that like keeps calling back. And
no, there's a limit for one. There's a fold, the whole thing transactions limit.
Yeah, that was because that would be bad. So how would you do flash loans in Near?
You don't.
Okay.
So I mean, you would have a Uniswap having a flash loan capacity, or this is what we're thinking, to have vaults. So vault would be something that travels, like that's on the runtime level, and it travels between contracts, and it has similar callback guarantees pretty much as. So you would like program a vault, like you say, it's either settles in this way or gets returned. Right. And so you package whatever resources you want in the vault, and
if it gets returned, it has do you have like a per block gas spend on the vault, like as it goes through each?
Yeah, you pretty much will like program, like you pretty much vault will be like a piece of programmable data that travels around, right? So right now data travels around without, like with just a call, but like what if you actually can program it so that it can execute? So
actually maybe this is a good analysis question. So like if we were to do a sandwich attack on Near, what's the number of, what's like if I drew like, you know, block height H, block height H plus 1, block height H plus 2.
Well, so right now, I mean, depends on how, like, so.
Can I like batch the transfers? Like
yeah, you can deposit everything, trade everything, and then withdraw everything.
Because like, say the attacker first does their trade, they say transfer A to the Uniswap contract. This one says transfer B, the user's token, so you can do that in one block.
You can do that in one block,
right. Yeah. Okay, so
but like an attacker would just already have all the deposits on the contract. Because you can have your internal balance on this contract. You don't need to.
Oh, I see. So you would have just already transferred.
Yeah, you just put all the money in, and then you just, when you see somebody executing, you just try to execute around them.
So you execute in the same block then.
Yeah, that's linearized.
Got it. Okay.
Yeah, so within this, you can have many like call executions pretty much happening within one block.
Are those it? But I force some serialization around them, right?
Yes, so this is where the fun starts. So each contract is its own quote unquote like chain rollup, whatever. But then they get batched into like actual shards, physical shards, which are actually, I mean, semi-deterministic. And then cross-contract calls are getting batched and received from different shards, and also like deterministic, but kind of determined by a previous block.
How do you guarantee that the validator executes the callback correctly on the next block? Like, are they slashed if they don't?
Yeah, that's just invalid state transition if they don't.
Okay, got it.
So like pretty much the way it works, so this is a block, right? So within the block there's chunks or shards. And then you have transactions here. And so this produces, we call them receipts, but this is just cross-contract calls. And so they're getting included in the beginning of the next. So these things will get included here.
I see.
So there's like actually two parts.
I see.
There's transactions and
the
receipts.
block header of the previous block includes the set of things that must be called first or something. Got it.
Yeah.
And but like, how can you? Is it possible that the number of these things have to get called here take up the entire next block?
So there's like there's always some limit to include more transactions, but so there's a queue pretty much been built, and it may take some time to like undo it. Yeah, process it.
So the user doesn't actually have that. So like, suppose there was like a order book.
Yeah.
And I had a liquidation from a lending protocol that like, took out the whole order book. It's possible that if I wanted to like trade on that order book, I submit a transaction, I'll be behind, you know, like 20 callbacks from that. Is there a bound on that time before, or like is there a bound on the space per block that's taken by the previous callback?
Yes. Yeah. So there's some space always for new transactions to come in, but.
Okay, so that's where you have some MEV. So if I know the new transaction space. Let's say I know there's a liquidation. Let's say I'm the liquidator, so I cause the liquidation to happen, and then I want my orders to get filled. I will just like add in new kind of like orders to the order book, such that some of these have to get executed in this block, right?
Yeah.
Non-zero number. Like if I look at, let's say this is like block space as like total. There's some percentage that is callbacks from last block.
Yeah, or like receipts. Yeah.
And how much is, and some new transactions.
Yeah.
What's the ratio?
I mean, so there's a limit on the whole block.
Yeah.
And then there's a minimum percentage for this. I don't remember what it is, but like, and then usually it's less than, and so it fills in with the rest.
Yeah, this is an interesting way of manipulating a TBOP oracle. So another form of MEV is like, let's say you have a Uniswap transaction and there's someone's using it as an oracle price, like they're marking a loan on another contract. If you basically change the price on Uniswap, so you paid to move the price up for a certain amount of time, you will somehow keep adding trades here that are callbacks, and you'll have to add some new transactions.
Yeah. So yeah, you can pretty much like try to push up the price, and while this gets executed.
While there's still more.
If there's more stuff scheduled to execute, yeah.
Right.
Yeah.
That's kind of interesting. This callback MEV, I don't think anyone's ever talked about.
No,
but it clearly exists. That like. So how does this ratio get chosen? Is that governance or is that?
Yeah, it's a configuration that governs.
So validators have to vote on a change to it.
Yeah.
Have you seen people taking advantage of this like in this way? Like,
not this. Right now I think there's some sandwiching that happens, but it's also hard because let's say.
Well, the sandwiching is capital inefficient here because you can't flash like. You can't really flash loan your sandwich.
Well, you can on a specific protocol application implementation that has internal balances.
Okay, so you're saying in the Uniswap contract I could put
it has so Uniswap contract is almost like its own chain where you can deposit money, trade, and then withdraw money, right?
Yeah.
Like that's why they are extra chains, right?
Yeah.
And you can do it in one transaction, but obviously it's less efficient than if you deposit, do a bunch of trades, and withdraw.
Right, but can I flash borrow as my deposit and then do the trades and then flash close? Assuming it's profitable.
There's no implementation in the current, but in theory you could. Yeah, in theory you could.
Okay, someone should do that. That actually, I feel like that would just make this process more efficient.
Yeah. In theory, because like this contract actually has a lot of liquidity itself, so it actually can borrow actually it doesn't even need the real money. Yeah, you can actually literally print the money. Because the tool will be within one of its execution.
Yeah, exactly. You should be able. So this is an interesting question in a protocol like Near, where I can think of it as like each app is almost effectively its own chain. Although there's some sequencing, there's
a pretty much synchronization that happens, right? That's really was like our point was if it's completely async, right? Which was like a lot of original sharding designs, it becomes like completely unmanageable. Right, because like as a user, you now have no idea what's going on.
Well, I mean, you already still do have the little.
You have some uncertainty.
Like as a user, you need to like the wallet needs to basically like resend if it doesn't make it into the. If you're on high priority, let's say you get into the callback, but you have no clue whether you'll be in the next block or 5 blocks away. You have to keep layering new orders and try to get into this. I mean, it's actually kind of interesting to think about what the other types.
But because in a way, this is a more optimized version of a multi-chain world, right? Like if you think of it, like this is each thing is multi-chain world. It's just you have kind of a single machinery to deal with it. But like you have this problem across, like say you have Cosmos with IBC, you have the same type of thing, right? You have like things sending money between, you can trade, you can withdraw, and so like a multi-chain MEV, that's what Nears already have.
Right. So what kind of so one interesting thing about multi-chain MEV, another kind of funny little allegory. This one again, I'm trying to do all the ones that don't need an email. This one doesn't really need
actually I was thinking about this. Yeah, so actually if this contract is refinance adds a primitive specifically for sandwich attacks.
Yeah.
Where you can you literally say, I'm gonna borrow X, trade like A to B or whatever, some set of executions, and then whenever somebody else trades this, I'll return it.
I mean, the interesting thing is this changes the dichotomy of this Uniswap pool, right? So like, let's just say we have R1, R2, which is like the reserves. Well, what are you borrowing when you're flash borrowing? Well, you're borrowing one side of this. So you're actually changing the price slightly when you borrow.
You literally just say, I'm going to drop but then this contract can just do it themselves. They can just give everyone the minimal price.
Right.
The minimal, like whatever the price that user said, the minimum they will be fine with, it can just give it to that and take all the money to itself.
Right.
Why doesn't it do that?
That's a great question. You should ask them why their token doesn't
No, but like what if a Uniswap just did that? Like it will always give the whatever minimal price or fail.
It is true. So that's what this like Penumbra type of thing does when they do batch auctions.
Yeah.
They effectively do. You could do it on the single transaction level. They just do it on a many transaction level.
But if we're talking about like generally the
having
if the contracts themselves
force that.
Yeah. Because then people will like actually optimize this. Because right now it said like to 5%. Or like 0.5%.
The problem is we're ignoring one user here, which is the liquidity provider, and they are losing out on this potentially.
But the contract can make money for liquidity providers with this. Like they can split the profit.
Right. They have to split.
Like in a way, like right now you have this like you get there's a price curve, right, like this, and you're saying if you're buying then the price goes up, if you're selling the price goes down, but the reality is you can just say this is like you'll be going from here instead, and this is your.
Yeah, the problem is the language that you design trades in Uniswap doesn't give you a price. You just say the language is trade size and slippage limit.
Exactly. Yeah.
It doesn't give you a price that you pin to.
Yeah.
If you added the price, you could sort of do this, provided that like, it is true. This is sort of like adding like stop loss orders.
Exactly. Well, yeah. Well, it's more like when you trade, you just say like, I trade A to B, and I want at least X of B.
Yeah.
Right?
Well, which is how slippage limits are defined.
Exactly.
This is how.
And so you just get always the X.
Yeah. So the problem is the user their transaction might fail many times because like someone front runs.
But this is true right now too when somebody is front running it.
Hopefully, yeah. As long as you can enforce.
So if there's efficient value extractors like Flashbot, you will always get X.
Yeah.
Otherwise, they're not efficient and they can extract more. So in reality, you're already getting this, except the money go to whoever runs searchers instead of LPs.
Right.
So why don't the swap protocols just give it to LPs and their token holders if they have the.
They could. I guess the weird thing about this borrow, this like, hey, I'm gonna take some of the reserves and like use it to do the sandwich, to auto sandwich, is that it doesn't work at very low liquidity. So like long tail assets are fucked. But then it also like doesn't work for really large trades because they will like wipe out. It'll have to borrow so much of this that it'll push the price. Like there is this trade-off between like how much you're willing to borrow to do the sandwich versus like the trade size, and it's unprofitable in some cases. But you're right that you could do it just on the trades. It's guaranteed profitable for LPs.
Yeah. So we just solved MEV? Is that?
No. There's other forms of MEV. There's
no, I mean this sandwich. We just solved sandwich text. Pretty much. All AMMs should just always return whatever minimum user said and make money for LPs.
Yeah, that's definitely true. They should just sandwich themselves. I mean, people have made these AMMs that have done that, but for some reason they've never been able to get liquidity because there's this like liquidity begetting liquidity effect of like if people's wallets are already routing to you, if like
no, I mean there's network effects.
There's network effect, that like I think somehow.
So you actually talked about like originally, and I know you wanted to flip to another topic, but the defining kind of it's through maximum permutation.
Yeah.
But like things like TWAP and other stuff that takes multiple blocks are actually not that.
Yes. So it's really the thing here is max over permutations, max over transactions you can add, max over transactions you remove.
Yeah. You postpone
such that the sum of all the transactions is less than the block limit.
But there's also a context of like can be doing this for multiple blocks.
Yeah. You again, that's true. Then you need to make sure this block limit thing takes an advantage of that. value of mempool.
Yeah.
So it is expensive. I do think these the amount people have. So one question you might say is like, suppose I gave you a Flash loan that, let's say Flashbots offered a service where they lend you collateral over a block. So let's say you're a searcher. So a searcher is a strategic user who does a sandwich or does a liquidation, whatever. Flashbot says, hey, we'll lend you 1 million. You can do a bunch of transactions. But it'll only be valid if we get back at least 1 million plus some interest.
Reward, yeah.
Right. But you can buy arbitrary amounts in the block. Now you could imagine just doing that repeatedly, and the cost of this TWAP attack just went down dramatically, right? So the question is, this is actually incentive compatible for the auctioneer because it's actually better for them to be lending you money, right? Because they actually don't earn any yield on right now.
Yeah, because it's
a
free
interest,
service,
right? And for them, this is free interest. So the question is, at what point does all the value go from the Oracle LPs to the auction? And my suspicion is, in the long run, the validators always hold the keys, and they can literally always do this, and there's no reason for them not to. And if you're accelerationist, validators should be selling these types of services.
But shouldn't validators be the oracles then? Because they hold the keys anyway.
Yeah, exactly.
May as well just provide the data.
Yeah. So EigenLayer, which is like this thing for ETH2 for restaking. So what it is like, let's say I'm an ETH2 validator, I've staked 100 ETH, and someone is like, hey, I'll pay you 5% a year if you take your 100 ETH in ETH2 and you restaked it in my Oracle protocol. So what that means is if I draw it, it's like I have my 100 ETH, I deposit it into a staking contract, and now I have 100 staked ETH. I'll call it SETH to separate it from STETH because that's slightly different. And what restaking does, instead it says, hey, put your 100 ETH in the Oracle contract.
That will actually stake it underneath?
Yes, and the Oracle deposits it there. And then when you, so the withdrawal address that the main protocol sees is the Oracle. But the Oracle is a smart contract that guarantees that when you call withdrawal, it atomically sends you back your withdrawal. Yeah. So now you basically get this pass-through where you can earn extra interest as the validator by basically delegating your stake to a contract that does go and put it in the main network, but then also earns fees from whatever people calling the Oracle function. So there's a sense in which that's the way I think that all of these services that validators could offer, like lending, you could basically make a lending protocol like this, that where the amount that's allowed to be lent effectively is like the protocol, say, takes, so let's suppose we had a lending protocol version of this, lend. They take 95 ETH and restake, and they take 5 ETH and put in the lending pool. And the idea is maybe this is getting you, 7% fixed, and the loans are getting you like 5 to 10% variable, right? And like you can choose how much you want to do that. And then you would have, then the validator would have the capital to like do this.
To like lend, yeah.
But then the TWAP Oracle completely is ruined.
But like what? I mean, but if we go further, we just go to add this on the protocol level where.
You could add these as services directly in the protocol.
Yeah, and then you can borrow any amount of anything.
Right.
If you return it back.
You can even flash mint, right? Where you mint.
Well, that's what I mean. You flash, you just borrow any amount, like infinite amount of anything if you return more of it.
Hey, UINT64 has a max, buddy.
Well, U256 to be clear.
U256 has a max also.
You can borrow as much as limit of the integers has been used.
Yes. Yeah. But like, I think this is actually what will end up kind of defeating a lot of like on-chain trading as oracles. Like, I think there's a lot of people trying to build lending protocols that use TWAP oracles, and the moment validators start doing, and like ETH has already gone this way. Proposer builder separation sort of screws over a lot of these things that want to use TWAP oracles.
Yeah.
So you might as well just shove it into the validator.
Yeah, there was no attacks yet on all the stuff that depends on TWAP. I think right now
the
validators can do whatever, right? They can just.
There've been a couple, and most of them actually just have to do with people's using bad TWAP settings.
Okay.
Because like obviously if they make the window too short, it becomes really cheap.
It's really easy, yeah.
And so like I think another kind of interesting liquidation game to consider is cross-chain auction design. So this is something I'm working on now, and it's formalized formally, but like there's one example in there that's kind of interesting. So suppose we have two chains, chain X, chain Y, and there's a AMM here that is trading X versus synthetic Y. Synth Y. And there's something here trading synth X, Y. Okay, so let's suppose the price here is P0, the price here is P1, P0 is less than P1. Let's suppose that there's validators. I should maybe draw them as little stick figures. There's validators.
Same validators of people.
They might not be the same. They might be the same. Who knows? And they can do one of three auctions. One, sell the arbitrage. So like, trade X for synth Y, go to Y, redeem it, trade Y for synth X, go across back. So you can price the auction, price the bundle in X, price bundle in Y.
Or price both.
Or sell the leg separately, yeah. And depending on the liquidity and the gas cost model, when you do this trade here, if you bid on them separately, you're actually bidding on how much you're going to change your gas cost here, because you're actually pushing down the price Y. So if there's this price difference is really big, then you actually can, as the auctioneer, earn higher revenue by pricing separately versus pricing in one or the other. And this is the type of stuff I think that like makes this cross-chain MEV stuff much more complicated. It's like, actually sometimes the auctioneer should be offering you very different sets of bundles, bidding languages.
Well, I mean, this is where you, like, ideally have some options that you can buy to like hedge your.
Sure. I mean, like,
hedge your latency.
I'm saying like that. There's certainly hopefully that, but for a lot of coins that's not true, right?
Well, I mean, so this is, I think one of the interesting things in general for any multi-chain stuff is, because like there's a latency, L that exists here, and so what you want some option for like 2L plus some epsilon that will guarantee you whatever you're doing here.
Yeah.
And so having like a facility that gives you such options, like efficiently priced.
Again, this is another thing that validators should be selling you.
Yeah. Especially validators that run across all the chains.
Right. So exactly. So the difference in value. So in a sort of no arbitrage world, which is obviously somewhat idealistic, but it's not that idealistic because the validators, if they're issuing the options, should be no arbitrage. Like, otherwise they fucked up. That means that they wrote their code wrong. Then in that case, if there are options, these three should all probably be priced the same, because these two will include options, right? But my point is right now that if you just look at the dexes, the way MEV is extracted is kind of is actually the way people are designing how you bid on these things changes their revenue, and I don't think anyone's very much solved that problem.
Yeah, I mean, I think that there's an interesting, like, if we're talking about validator, right? Like right now, it's just running like your regular node.
Yeah.
And so already with Flashbots, the idea is like you run something that like proposes blocks. Sidecar proposes block. So the question is like, should this be kind of a standardized facility to allow like for kind of customization of the, almost like a block logic, right? Like for flash mints and kind of all these things. And
I think that's inevitable. This is the direction. I think all the Cosmos MEV stuff is moving this direction. I'm gonna guess near MEV will move in this direction. This is where it's different than ETH, because ETH is doing first proposer-builder separation, which kind of complicates doing these sidecar things a bit. Because the block, so the proposer is the person who gets drawn from the stake distribution. The builder is the person who proposes a block. And so you have this auction where the proposer is given a bunch of blocks. They can't see what the transactions are, but they're bidding on, a particular block. So it's like,
no, they're just picking whatever who pays them more, pretty much, and they just
they
pick
should
that
be.
block.
But I mean, there's some weirdness here in that. And I don't know why Flashbox people don't believe this, but like the proposer and builder could easily collude by being the same person, right?
Which they are.
They
right
usually
now.
are, right? Like,
yes. So there's like builders who propose.
Builders propose a block.
Propose a block, which is why it's confusing.
Yeah.
You would expect proposers to propose a block.
Correct.
And then the validator, let's just call them, is the one who actually picks. And so like naturally, I mean, ideally they should pick whatever pays them the highest.
Yes.
But they can, if they are the builder, then
there's some incentive for them to choose that.
So,
well, they might want to choose the cheaper one because they have a bunch of their own. Like,
well, there's like extracted value here, which is higher than this price,
right.
And so
this again gets at this fact of like fair ordering is fucking stupid. Like this thing will never be compatible with this idea that there exists some global like. Kenneth Arrow won the fucking Nobel Prize for proving this impossibility theorem for ranked voting, and like somehow we still want to like shove ourselves into like pretending that's not just like a fact of reality.
So there's no fairness.
There's
that's
no
pretty
fairness.
much. Sorry for destroying your world. There's no fairness.
There's a trade-off of fairness.
Yeah.
There's a big problem in machine learning too right now. Big problem in both machine learning and crypto. So like I actually think that's where the intersection of research is right now. Is like the fairness thing of like. How much fairness do you trade off for accuracy / cost and latency and like very hard problem. But
well, that's why there's.
But I do think people will make a node where there's sort of like a DSL, or that like lets you like say, hey, I'm going to use this mainnet contract as my restaking mechanism, and like you deploy these contracts like Oracle, lending, whatever, that basically guarantee the execution for the validator.
Yeah, but well, I don't think you need a restaking contract. You just literally have some. You just say like there's a facility of like pre-block, post-block logic.
Yeah.
That everybody the whole blockchain just votes that we can accept.
Yeah.
This piece of code to run, and like in Cosmos, it's like everybody does that all the time.
Well, I think the restaking thing's kind of important because I know the pre-block, post-block header thing there is like a little bit that makes sense, but
I think like in Cosmos they just have that they literally have that two pieces of code.
I think the interesting thing here is that the lend contract may actually want to source liquidity not from the validators, right? The lend contract might just be like, hey, it's the normal Aave pool.
Yeah.
And you're just using the Aave pool.
That's if you don't have just flash mint. If you have flash mint,
you're
and
fine.
that's what I'm saying. Like if you have just like facility to do whatever.
Yeah.
I mean, it's that's where like who audits that code and stuff like this, but.
Yeah.
But like generally saying, right? I mean, this is where like if we had programmable resources, then you can have a flash mint in the resource where like in X blocks it needs to come back.
But I guess my question with the design you were saying earlier of like have to wait each block for the like how does flash mint work? Because I can flash mint, but then the flash mint is stuck. Oh, well, you need this like context vault.
Yeah.
Thing,
so this thing, that's what I'm saying. It's programmable. There's like a piece of logic there that says. In X blocks, this thing needs to come back and call this function that will like flash pretty much mint it, burn it. And so it doesn't matter where this resource ends up. Well, that's where the guarantee by the runtime.
I see. Okay, so
in runtime, there's a new place where it records all the resources that are there and it iterates over them and says like, is any of these resources need to go back?
It also says basically takes a lock on all these resources.
Exactly.
Yeah.
This is a lock mechanism. It's a mutex of resource that you can travel around. This is how we were solving the train and hotel problem. And we have not implemented this because it is more complex. But actually, Move is doing this. This is where it gets interesting because Move is actually a programming language that has the resources already.
Yeah.
Which are like have conditions around
I do think the problem with this stuff is like the Uniswap style, like global state, everyone is shitting in the same pool when you're executing doesn't work very well here because you have to have many of these running concurrently for each user in some sense, which can be like a pain in the ass. So you need to build this stuff to like manage like all the users like state traipsing, and like then when there's like
when
two people are touching the same lock, like you have some rules.
But this is where like usually something on Uniswap will just be one chain contract account thing where you just synchronize everyone, trade it, and desynchronize.
But I just mean for developers, that's quite a bit of overhead if they have to think about that. They want to write fucking JavaScript, man.
They do. That's why we have now JavaScript.
They don't want to write this type
Well, in JavaScript, you do have callbacks, and if you're writing, this is literally how microservices work. To be clear, this is like you have each contract on Near is a microservice with a database, and it receives incoming calls, and it has callbacks.
But the question to me is actually more like the lock on the state that's touched
is
like
based on how you want it. It's a developer.
Right.
Okay. That's why we wanted to add some facility, like standardized lock facilities, but we haven't.
Is there a way to like, wait, can I control whether I have a view-only resource versus mutable resource of like?
You as a developer can implement whatever you want. You can literally resolve your own locks and everything. So.
Okay, because that makes sense. This seems like there's more MEV here, honestly, than there is in ETH. Like I know all the move people are like, oh, we have less MEV bullshit. Like this actually seems like there's way more of like
for the resources,
the the sequencing. Like suppose I have like 5 resources. Let's suppose there's state 1, state 2, state 3, and like calculation 1, calculation 2, and we have 5 people, and they let's suppose we have this sort of like complete bipartite graph on this, and each of them is taking some path. Like one is doing that, one is doing that, one is doing that, and they have some contention, right? Like they'll reach the same state. The resolution of those contentions is either random, but the randomness is not really random there because it's if you know the validator code, you can figure out they have to come to consensus on it. So there must be some deterministic source of that. So you could try to basically simulate ahead the previous the resource.
Unless you pipeline it, then it's the next block. So this is where like in our case we actually have a 1 bit of like validator can only affect 1 bit of randomness, right? By not producing a block, which then actually corrupts their ability to do anything. And we actually had a fully non-biased VRF implemented but not launched.
Well, how come there's one thing I haven't understood, because there's so many benefits to application developers, is why no one has a VRF at the application level. Because like to some extent, the thing you were describing earlier, where we're like, hey, we will. We'll let you borrow a little bit before the contract does it itself, is a sort of form of like, hey, the contract is collecting its own MEV, or like there's application-specific MEV. But one of the things is like that's not quite easy to do right now. And one thing that would make it easier is actually having just like a VRF you could call in your contract that's tied to the consensus.
So we have that because when you submit a transaction, it gets included and then it gets executed.
Okay.
So by the time it gets executed, you already had something that was like a consensus
but
here
I'm just
and have a randomness
people haven't
source.
made like numpy.random for consensus randomness. Like I want to sample Gaussian. I want to do
You can do that on Near.
I know, but someone should actually just make the library because like I feel like that will actually give application developers a lot more easy control over avoiding these.
So you're just saying like, just give a random amount back pretty much within the range.
Right, but with some distribution. Like you have a slippage and you just say, well, we're gonna give you random amount. Well, so we wrote this paper proving how to get differential privacy, which is sort of like a way of, you can show for these AMMs you can't ever give pure privacy even if you had a ZK proof blocking the reserves, because if you see the prices, you can always invert the prices because the functions are deterministic for how they change. So the question is, how do you add noise such that, if I add X bits of entropy to your trade, which change your price by some amount of, there's some bits of entropy to the random price, how do I make sure that someone can't infer what your trade size was with more precision than X, but then I also don't move your price more than Y, right? So there's there's like the trade size space, and then there's the sort of, price. And I want to add randomness, so you're in here, but then I also don't want this thing to be really large, right? And so there's this trade-off. And if you had different distributions, you can like add noise here with certain distributions to guarantee that this thing is bounded.
All right. Well, there's a project right there for someone to build.
I think the library thing might be first. NumPy.random.
Well, that's what I mean. Yeah, because there's a source of randomness, you just need to then build distributions.
Yeah. Or just you can just copy.
You can actually run NumPy on here.
Right, you could just copy that and just make sure it uses the correct.
It's a C code, so you can just run that.
You just need to make sure it gets, well, the problem is your VRF's 256.
256 bits, yeah.
You're going to need to like convert that, shuffle that into numpys. But my point, and you probably want 256-bit randomness, so you might want to rewrite those to support U256. But I think there's like lots of stuff like this, unexplored territory for people.
All right. Well, lots to build. There's and lots to fix with the existing protocols. So
I mean, look, he didn't think we'd have an hour of MEV content.
All right, awesome. Thanks, Tarun, and please check out all the videos, like it, subscribe. You know, the usual YouTube stuff that I don't know what to do, but thank you.
See, I told you we'd find
something. I know, I mean, I'm sure we can talk for like many hours, to be clear. Like.
I feel like we got through a lot of shit.
Yeah, no, it's good.